Today we're going to start unit number 4. And with unit number 4, it's actually made up of 3 smaller units. The first of those units is about torque. So torque is a word that maybe you heard before, but you're not quite sure what it means. So let's start with the idea of what is torque. Torque refers to a force's ability to make something rotate. So if I wanted to get into my peanut brittle and I apply a force to this lid, I have to know how effective that force is going to be at creating torque. If I had something like a little screw and I wanted to tighten or loosen it, okay, or a little thing here that I want to tighten or loosen, we're talking torque. Anytime we're talking about trying to get something to rotate, the idea that comes up is torque. It's the ability of a force to make something rotate. Okay, so here we have a little pivoting hinge that'll make this wooden dowel move almost like the minute hand on a clock. So I want to create some torque. I want to get this thing to rotate. There are 3 things that I can change about the way I apply my force that's going to generate more torque for me. So think about what those 3 things could possibly be. Okay, the first of those things turns out to be location. Okay, so if I push here, I am very ineffective at trying to get it to rotate. If, on the other hand, I push out here, it rotates very easily. If I push somewhere in the middle, I can do it, but not as easily. Okay, so location. And actually, you got to measure from the pivot point. So factor 1 is the distance you are from the pivot point. The farther you can get from that pivot point, the more torque you're going to generate with your force, with your push or pull. Okay, so that's factor number 1. Okay, we can see that real easily because I put 2 hooks on my side door, one at position 1 and one at position 2. You see the hinges, that's where the pivot point is. And I attached a string to try and pull the door open once I loosen the handle. Pulling at position 2 versus pulling at position 1, 2 was much easier because I'm farther out from the hinges. That's why they put the handle to open the door as far from the hinges as possible. It makes it easier to create rotation. So if I had a door, we're looking from above, here are the hinges. I can apply my force at A, B, C, D, or E. E would be the one that's going to create the most torque. It is the farthest distance. Make sure you measure your distance in meters. Factor number 2, I'm going to apply the forces at the very end, so I get the most torque based on distance. Factor number 2 is how much force I actually apply. So if I apply a tiny little force, I'm not generating much torque. The more force I apply, the more torque that I actually am able to generate. Okay, so factor 2, the strength of the force. Factor number 3 is the angle that you apply your force. This angle is most effective, 90 degrees. This angle is totally ineffective because now I'm pushing it into the hinge and I'm not creating any rotation at all. So 0 degrees or 180 gives you no torque. 90 gives you the greatest amount of torque. Okay, so we have 3 factors. We want to push as far from the hinge as possible, the pivot point. We want to push as hard as possible, and we want to make sure that the push is at a 90-degree angle to our radius, to our distance. Here you can see me using the string again, pulling at 90 degrees versus pulling at maybe 30 degrees, and 90 is way more effective at getting the door open. Okay, so the formula for torque, and we can see the guy trying to loosen the bolt on the bicycle tire using his wrench. Those factors would be, and the formula would be torque equals RF. Note the symbol for torque is not our normal English T, okay, which I like to have every morning. Okay, instead it is a Greek letter called tau, and it indicates torque. It's kind of like the pi symbol, but with just one leg. Radius, measured from the pivot point, and that's going to be measured in meters. Force, perpendicular. This little symbol tells you that the force has to be perpendicular to your radius, and that's going to be measured in newtons. So when you calculate your torque's going to come out in Newton meters. Don't say per, you're not dividing, you're multiplying, so just slur them together. Newton meters. Okay, torque is measured in Newton meters. In the English system, you'll sometimes see it measured in pound feet, or sometimes they'll write it this way, it doesn't matter. Foot pounds. Okay, so you can have pound feet of torque or foot pounds of torque, but the international standard is Newton meters. So if you were to take a look at this, identify the pivot point, measure the radius, measure the force, multiply that force by the radius, and you've got your torque. Again, the force has to be perpendicular to the radius when you're doing your calculation so that you can get your torque. If the force is not perpendicular, we'll see how to deal with that in just a little bit. This idea of torque kind of harkens back to the days of Archimedes, back in the 200 BC time. He's from Syracuse, which is in modern-day Sicily. And he realized that by increasing the radius, you could increase your amount of leverage, your amount of torque, the effect of that force that you're applying. So small forces could actually have big effects by using the idea of increasing your radius. Okay, so we could see this if we're trying to fix our rollerblades. We have our little Allen wrench, and you could hook it up in one of two different scenarios. The one that is going to generate more torque is case number one. This is your pivot point. You want to apply your force as far away from that pivot point as possible. So in this case, you're only a small distance away from the pivot point. Again, this distance doesn't matter because you're applying your force horizontally. So you want your horizontal distance going outward, and case one is better than case two. All right? So if you tried to do it with case two, you'd realize you need a heck of a lot more force to turn that. In case one, a lesser force would be able to generate the same or maybe a greater torque. We can see this with my doorway. If I try to prop it open with a stool, if I put the stool in the middle of the door, it's very ineffective at holding the door open because it's not going to generate a lot of torque. If I want to keep the door open, I want to move the stool as far away from the hinges as possible. We can see this if you ever have to change a flat tire. Okay? You might be able to do it by putting all of your mass on it, but if somebody uses a really powerful tool and gets that lug nut on there really tight and you can't loosen it, you want to do something like this. So you take your wrench, you put it on there, and you use a pipe to increase your distance. And by increasing your distance, you're able to generate a lot more torque. So again, the factors, the amount of force, you might be able to generate more force with your legs, so you can get some extra torque, but even if you can't get it off with your leg, you can increase your radius, and that would give you more torque, more leverage, and a greater chance of loosening something that is seemingly stuck. Okay, so again, the steps to calculate torque. If we have this board, you find the pivot point, you measure the radius, you measure the force, you make sure your force is perpendicular, and you just multiply them together. Okay, so in this one, we would just do torque equals RF. The R would be 0.1, the force would be 40, and we would get a torque of 4 Newton meters. This happens to be making it rotate clockwise, so technically it should be -4. As we learned, clockwise is negative. All right? This number is just telling you the size of the opening here and has nothing to do with your actual torque. Okay, by moving this farther out, we generate more torque. So this time, our radius is 0.2. And this time we would get 8 Newton meters. Again, clockwise, so negative. You don't need to put the negative if you just write clockwise. So one or the other, don't do both. Here we have our force and we're applying it right in line with the bolt. So this would create 0 torque. We have 0 distance. Doesn't matter how hard you push, if you're pushing at this location, that generates no torque. Here we are pushing all the way at the end of the wrench, but again, we're pushing parallel to the radius, so we generate 0 torque. Finally, how do you deal with it if you're not 90 degrees, but you're not 0 degrees? You just take your force, you create a right triangle, and you use your trig functions to figure out force X and force Y. You really don't need to do both, because when you're looking at which force is perpendicular, it would be Y. Force Y is perpendicular to your radius, so you'd use 0.25. You would use cosine of 30 times 40 as your force, and you would generate your torque. Once again, this is going to rotate clockwise. So indicate that by either saying clockwise or by putting a negative. All right? Finally, if someone asks you for net torque, that means you have multiple forces all trying to create rotation. So this is like a merry-go-round that you might find at a playground. And we have a bunch of different forces that are trying to get it to rotate. So what you would do is you'd find the torque from each one separately. Find the torque, 0.35 times 2.1. Find the torque from this one. And finally, find the torque from this one. Okay, do you add or do you subtract these torques? Well, you gotta look at what direction they are. So hopefully you could see that this one is trying to get you to go counterclockwise. This one is rotating you counterclockwise. And this one is trying to rotate you clockwise. So you would add the two counterclockwise and subtract the clockwise. All right? And that would give you your net torque. Make sure you take into account direction so you know whether or not you're adding or subtracting your torques. Again, the pivot point for the merry-go-round is right in the center. So you just do the radius times the force. All the forces are at right angles, so you don't have to worry about using any trigonometry. So to summarize, torque talks to us about a force's ability to make something rotate. Bigger distances will make it easier for things to rotate. A 90-degree angle between the radius and the force will generate more torque, and a greater force will generate a greater torque.